The instruments themselves were purpose-built for exactly the discoveries described here, even though nobody expected them to still be running when those discoveries happened. Each spacecraft carries a magnetometer on a long boom to keep it away from the spacecraft's own electrical interference, measuring the direction and strength of magnetic fields. The instrument that would eventually catch the strange non-rotation of the field at Voyager 1's heliopause crossing. A plasma science instrument measures the density, velocity, and temperature of charged particles, the primary tool for tracking the solar wind itself. Though it stopped working on Voyager 1 in 1980, meaning scientists had to infer solar wind behavior around Voyager 1 indirectly for decades using its other instruments. A cosmic ray subsystem and a low-energy charged particle instrument together tracked the particle populations that would reveal the gradual rise in galactic cosmic rays and the corresponding fall in solar particles as each spacecraft approached its crossing. And a plasma wave subsystem listens for the electric field oscillations produced when the solar wind or interstellar plasma vibrates, the instrument responsible for detecting the tsunami waves rippling through interstellar space years after each crossing. None of these instruments were designed with the heliopause specifically in mind, since nobody expected the spacecraft to survive long enough to reach it. They were general-purpose scientific tools, robust and simple by necessity, that happened to still be functioning and sensitive enough to catch phenomena nobody had thought to design for. That's arguably as much a triumph of 1970s engineering conservatism as any single measurement the instruments returned. Engineers of that era, working without the benefit of decades of spaceflight heritage to lean on, tended to overbuild, add redundant backup systems for nearly everything, and avoid untested components wherever a proven one would do. It made the spacecraft heavier and more expensive up front. It's also very likely the reason both Voyagers are still transmitting data 5 decades after a mission planned to last 5 years. This is the technology that discovered what lies at the edge of the solar system. Voyager 1 reaches the termination shock on December 16, 2004. The spacecraft is at 94 AU from the Sun, 8.7 billion miles. Scientists had predicted the termination shock would be at 75 to 90 AU. Voyager is already beyond that range. The crossing isn't clean. Voyager detects the shock on August 1, 2002, at 85 AU. Then the shock moves outward, and Voyager finds itself back in supersonic solar wind. The signatures of the shock disappear. In 2003, Voyager detects it again. The shock washes over the spacecraft, then retreats. Finally, on December 16, 2004, Voyager crosses and stays in the slower, denser plasma beyond. This breathing motion is caused by solar activity. Strong solar outbursts push the shock farther out, while quieter periods let it drift back in. The boundary is dynamic, not static. Voyager 2 crosses the termination shock on August 30, 2007, at 84 AU, 7.8 billion miles. That's about 10 AU closer to the Sun than where Voyager 1 crossed. If the boundary were spherical, both spacecraft should cross at roughly the same distance. This is the first solid evidence that the shape is wrong. The heliosphere isn't a simple bubble. It's compressed in some directions, extended in others. Voyager 1 is heading toward the nose, the direction the Sun moves through the galaxy, which is compressed like a bow wave in front of a moving boat. Voyager 2 is heading more toward the side, where the boundary is less compressed. Scientists had suspected this might be the case. Now they have proof. After crossing the termination shock, both Voyagers enter the heliosheath. This is supposed to be straightforward. Slowed solar wind plasma flowing outward and sideways, turbulent but predictable. A transition zone expected to take Voyager 1 about 5 to 10 years to cross, reaching the heliopause around 2015 at roughly 100 to 110 AU. But starting in 2010, something unexpected happens. Voyager 1 begins detecting increasing levels of galactic cosmic rays, intensity that was expected to rise sharply only at the heliopause, in the middle of the heliosheath. At the same time, lower-energy solar particles are decreasing, when they were expected to disappear only at the heliopause, not fade beforehand. Instruments still detect solar wind plasma. The magnetic field still has the characteristics of the Sun's field. So what's happening? In June 2012, Voyager 1 detects something completely new, a region where the magnetic field lines run directly radial, pointing straight outward from the Sun, not tangled, not twisted, perfectly organized, with particles flowing along these field lines in both directions, solar particles outward, galactic cosmic rays inward. Scientists call it the magnetic highway. No model predicted this. The leading theory is that the Sun's magnetic field is connecting directly to the galactic magnetic field, letting particles flow freely both ways, like a bridge between two otherwise separate regions. Voyager 1 spends about 2 months in this magnetic highway. Then, on August 25, 2012, everything changes. Solar wind particles essentially vanish. Cosmic rays jump to a high, steady level. But the magnetic field direction doesn't change. It keeps pointing the same way it did throughout the heliosheath. This causes confusion. Some scientists argue Voyager has crossed the heliopause, since the disappearance of solar particles and surge in cosmic rays suggests it. Others argue the lack of magnetic field rotation means it hasn't. The debate continues for over a year. Finally, in September 2013, NASA officially announces that Voyager 1 crossed the heliopause back in 2012. The spacecraft was at 121 AU, 2 billion miles from the Sun, far beyond where models predicted, not 90 to 100 AU, but 121 AU, 20 to 30% farther than expected, 2.4 billion miles beyond the predicted boundary. This is shocking discovery number 1. The heliopause isn't where scientists thought it would be, and it's not a small error. It's billions of miles off. This means either the solar wind is stronger than models assumed, or the interstellar medium is weaker than estimated, or both. Later analysis suggests the local interstellar medium is somewhat less dense than scientists thought, not dramatically less, but enough to shift the balance point outward by 20 to 30%. This matters because the heliosphere shields the inner solar system from galactic cosmic rays, and a larger heliosphere means better shielding, potentially affecting cosmic ray exposure on Earth over geological time scales. Scientists also expected the heliosphere to be roughly spherical, maybe elongated into a tail, but basically symmetric. The reality is different. The heliosphere is shaped more like a bullet or teardrop. The front, where the Sun moves through the interstellar medium, is compressed into a blunt nose. The sides are flattened. The tail stretches out behind for potentially hundreds of AU. Voyager 2 crossed the heliopause on November 5, 2018, at 119 AU, heading in a direction more toward the flank than the nose. Both spacecraft crossed at roughly the same distance from the Sun, which tells us the heliosphere isn't dramatically elongated at the sides. The asymmetry is more subtle, driven by compression at the nose from the Sun's motion through the galaxy. Outside the heliopause, there should be a bow shock in the interstellar medium, similar to a bow wave in front of a boat. Models predict this shock at around 140 to 230 AU, but given how wrong the models were about the heliopause, the bow shock could be anywhere. The Voyagers haven't reached it yet. The shape matters for cosmic ray access to the inner solar system. With a bullet shape instead of a sphere, cosmic rays can penetrate more easily from some directions than others, and the tail might provide an easier path for cosmic rays to reach us from behind. The shape also isn't fixed over time. The Sun is moving through a region called the local interstellar cloud, a slightly denser patch of the interstellar medium a few light-years across. And in thousands of years the Sun will move into a different region where interstellar pressure differs, changing the heliosphere's shape and size. The Voyagers are giving us a snapshot of the boundary as it exists now. This is shocking discovery number 2. The shape is wrong. Asymmetric, dynamic, influenced by the Sun's motion through the galaxy, not the simple bubble scientists predicted. Scientists also expected the crossing itself to be relatively clean, a boundary where, over a few weeks or months, solar plasma disappears, cosmic rays increase, and the magnetic field reorients. Instead, Voyager 1's approach to the heliopause takes over 2 years, including the unpredicted magnetic highway, and when it finally crosses, the magnetic field doesn't rotate at all, because, scientists eventually conclude, the galactic magnetic field happens to run roughly parallel to the Sun's field in that particular region. Pure coincidence. Voyager 2's crossing is different. It happens over about 1 day, much faster than Voyager 1's multi-year transition, and it does show a clear rotation in magnetic field direction, about 20 degrees, not dramatic, but measurable. The difference comes down to location. Near the nose, where Voyager 1 crossed, the heliosphere is compressed and the boundary structure appears more complex, with phenomena like the magnetic highway perhaps more common there. Toward the side, where Voyager 2 crossed, the boundary is sharper and the transition faster. Both spacecraft also detect oscillations after crossing. Voyager 1 briefly detects solar particles again in August 2013, nearly a year after its initial crossing, then they disappear again, the boundary washing over the spacecraft, then receding in response to solar activity. A pressure pulse from a solar storm can take a year or 2 to reach the heliopause and temporarily push it outward past a stationary spacecraft before contracting again. This is shocking discovery number 3. The transition is complex, prolonged, and dynamic, multiple crossings, the magnetic highway, oscillations. Nothing like the clean boundary scientists predicted. The boundary of the solar system isn't fixed. It's not a line you can draw and say, here it ends. If you're sitting at 120 AU, whether you're in the solar system or interstellar space can depend on when you ask. Voyager 1 is the first spacecraft to directly sample the interstellar medium. Before Voyager, all knowledge of interstellar space came from remote observations, spectroscopy of distant stars, radio observations of hydrogen clouds, theoretical models. Voyager measures it directly. The density is about 0.08 particles per cubic centimeter. The best vacuum chambers on Earth achieve densities around 1 million particles per cubic centimeter, so interstellar space is a better vacuum than we can create in our best laboratories. But it's not nothing. The temperature is roughly 54,000 to 90,000 degrees Fahrenheit, which sounds hot, but temperature measures average kinetic energy per particle, not heat content. With so few particles, even high temperature doesn't mean high heat. An astronaut in interstellar space would freeze, not burn, since there aren't enough particles to transfer heat efficiently. The pressure is extraordinarily tiny, roughly 100 trillionth of Earth's atmospheric pressure at sea level, yet it's enough to balance and stop the outflowing solar wind at the heliopause. Voyager also detects plasma oscillations in the interstellar medium, waves of compression and rarefaction traveling through the plasma. In 2012 and 2013, Voyager 1 detected several bursts of these oscillations, and the frequency let scientists calculate electron density. Different measurements give slightly different values, showing the density varies by 10 to 20% over distances of just a few AU. Denser regions push harder on the heliosphere from that direction, less dense regions let it expand farther. The interstellar medium is also magnetized, carrying a magnetic field that's part of the galaxy's overall structure. Voyager 2 measures its strength at about 50 nanotesla, roughly a millionth as strong as Earth's surface field, but over vast distances. Even this weak field has significant effects, shaping plasma flow and accelerating cosmic rays. None of these properties match predictions exactly. This is shocking discovery number 4. Interstellar space properties don't match the models. The first direct measurements reveal differences in density, temperature, pressure, and magnetic field. Small differences, but enough to matter. One of Voyager 1's most surprising findings is what scientists call tsunami waves, shock waves traveling through the interstellar medium, triggered by the Sun. When the Sun produces a powerful outburst, a coronal mass ejection or a strong solar wind burst, that pulse travels outward through the heliosphere. When it reaches the heliopause, it hits like a hammer, launching a shock wave into the interstellar medium. These waves travel at the interstellar sound speed, roughly 60 kilometers per second, much slower than the solar wind, but fast enough to cross several AU in a year. Voyager 1 detects the first tsunami in October and November 2012, then a second in April and May 2013, a third in March 2014, and a fourth in 2015. Each wave traces back to a solar outburst years earlier. The pulse travels outward at supersonic speed through the heliosphere, hits the heliopause, and launches a shock wave into interstellar space, which Voyager then detects months or years later. This reveals that the Sun's influence extends far beyond the heliopause, not as solar wind plasma, which is confined to the heliosphere, but as pressure waves that travel through the interstellar medium itself, possibly tens of AU beyond the boundary before dissipating. The detections also confirm Voyager had genuinely crossed the heliopause. The waves arrive as shock waves propagating through interstellar plasma, not as direct solar wind pulses, which is what Voyager would detect if it were still inside the heliosheath. This is shocking discovery number 5. Tsunami waves from solar storms propagate through interstellar space. The Sun's influence reaches farther than anyone imagined. Perhaps the most puzzling discovery involves the magnetic field's orientation. Before Voyager 1 crossed, models predicted the galactic field would be oriented differently from the Sun's field, since our region sits in the Orion arm, and the galactic field should run roughly parallel to the spiral arm structure. Crossing the heliopause should have shown some significant rotation, marking the transition from a Sun-dominated to a galaxy-dominated field. Voyager 1 detects no such change. The field direction after crossing is essentially the same as before, causing months of confusion until scientists conclude that the local galactic field just happens to run roughly parallel to the Sun's field at that particular crossing location. Pure coincidence. Voyager 2's crossing, in a different location roughly 100 AU away, shows a small but measurable rotation of about 20 degrees, revealing that the interstellar field near the Sun isn't uniform, like a bar magnet, but structured and twisted by plasma currents and stellar influences. With only 2 data points, separated by over 100 AU, it's difficult to extrapolate how the field varies in other directions. This matters because the magnetic field guides cosmic rays, like channels, affecting how easily they penetrate into the heliosphere, and by extension, cosmic ray exposure on Earth, which influences atmospheric chemistry, isotope production, and possibly cloud formation over geological time. This is shocking discovery number 6. The magnetic field orientation was unexpected, and it varies meaningfully between 2 points barely 100 AU apart. Galactic cosmic rays are high-energy particles, mostly protons, accelerated by supernova shock waves, pulsar winds, and other violent events, carrying energies from millions to trillions of electron volts, some beyond what the Large Hadron Collider achieves. As Voyager 1 moves through the heliosheath, cosmic ray intensity gradually increases. As expected, deeper into the heliosheath means weaker shielding. But the directional distribution is surprising. Instead of roughly equal intensity from all directions, there's clear asymmetry, with enhancement from some directions and a deficit from others. After crossing the heliopause, cosmic ray intensity jumps by about 10 to 20% compared to the heliosheath, confirming that even the outer heliosphere provides meaningful shielding. Voyager 2 confirms the same pattern after its own crossing. Interestingly, both spacecraft detect lower cosmic ray intensity from the direction of the galactic center. Counterintuitive, since that region has the highest star density and the most supernova explosions. One explanation is that the galactic magnetic field is stronger toward the center, trapping and scattering cosmic rays trying to propagate outward, so fewer reach our local region from that direction. This remains active research. This is shocking discovery number 7. Cosmic rays come preferentially from unexpected directions. The source distribution doesn't match simple models. Understanding that distribution isn't purely academic. Cosmic rays that make it past the heliosphere shielding and into the inner solar system interact with Earth's atmosphere, producing cascades of secondary particles and trace isotopes like carbon-14 and beryllium-10, which get incorporated into tree rings, ice cores, and ocean sediments and preserved for tens of thousands of years. Researchers use these isotope records to reconstruct how cosmic ray flux at Earth has varied over time, and those records show real variability, some of it tied to Earth's own magnetic field changes, some tied to the Sun's roughly 11-year activity cycle, and some potentially tied to longer-term changes in how well the heliosphere as a whole is shielding the inner solar system. The exact process the Voyagers were able to measure directly for the first time at its outer boundary. There's also an open, actively debated question about whether cosmic ray flux influences cloud formation in Earth's atmosphere, since cosmic rays can ionize air molecules, and ionization may play a role in seeding the droplets clouds form around. The effect, if it exists at all, appears to be small compared to other drivers of climate, and the topic remains genuinely contested among atmospheric scientists. But it's one more thread connecting a measurement made 11 billion miles from Earth to processes happening in Earth's own atmosphere. A reminder that the heliosphere isn't just an abstract boundary out at the edge of the solar system. It's actively shaping the radiation environment every living thing on this planet has evolved within. Tonight, we're going to explore one of the most remarkable journeys in human history. 2 spacecraft launched in 1977, designed for a 5-year mission to study Jupiter and Saturn. They're still operational nearly 50 years later, billions of miles beyond their original destination. And when they reached the edge of the solar system, they discovered something shocking. The boundary was 2.4 billion miles farther than every scientist predicted. The shape was completely wrong. The magnetic field behaved in ways no one expected. And the space beyond had properties that contradicted every model. 7 major discoveries that proved we didn't understand our own cosmic neighborhood. By the end of tonight, you're going to understand how 2 spacecraft built with 1970s technology rewrote our understanding of where the solar system ends and interstellar space begins. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now let's begin. The year is 1977. NASA launches 2 identical spacecraft on what everyone expects to be a 5-year mission. Voyager 2 lifts off on August 20th from Cape Canaveral. Voyager 1 follows on September 5th, taking a faster trajectory that will allow it to reach Jupiter and Saturn first. The names reflect their arrival order, not their launch sequence. Each spacecraft weighs 1,820 pounds. They stand 12 foot tall, and they carry a suite of instruments designed to study Jupiter and Saturn, the two largest planets in our solar system. The mission very nearly didn't happen in the form it eventually took. In the late 1960s and early 1970s, NASA and the Jet Propulsion Laboratory had studied an even more ambitious Grand Tour program involving as many as 4 separate spacecraft built specifically to take advantage of the rare planetary alignment and visit all the outer planets across multiple launch opportunities. That original, larger program was canceled in 1972 due to budget constraints, a casualty of tightening federal science funding after the Apollo program wound down. What survived was a scaled-back mission, initially named Mariner Jupiter-Saturn 1977, built using spacecraft technology derived from the successful Mariner probes that had already explored Venus, Mars, and Mercury, but repurposed and upgraded for the far harsher radiation and lighting conditions of the outer solar system. It wasn't officially renamed Voyager until roughly a year before launch, once it became clear the mission's ambitions and its potential to extend beyond Saturn to Uranus and Neptune if the spacecraft survived, had outgrown the more modest Mariner name and the incremental extension of an existing program. That flexibility mattered enormously later, since it meant Voyager 2's eventual continuation to Uranus and Neptune was never guaranteed by the original mission plan. It became possible only because the spacecraft kept working well past its formal requirements, and because NASA leadership was willing to keep requesting funding, one extension at a time, for a mission that had already technically completed its primary objectives once it left Saturn. The mission is called the Grand Tour, taking advantage of a rare planetary alignment that occurs roughly once every 176 years. This cosmic arrangement allows the spacecraft to use gravity assists, slingshotting from one planet to the next, to visit all 4 outer giants, Jupiter, Saturn, Uranus, and Neptune, in a single journey. Without this alignment, visiting all 4 planets would require separate missions and far more fuel than any rocket could carry. The planets have arranged themselves perfectly. NASA seizes the opportunity. The original plan is simple: 5 years to study Jupiter and Saturn, then drift into the outer solar system as the power fades and instruments go silent. No one expects these spacecraft to last beyond their warranty. No one predicts they will still be operational in 2026, nearly 50 years later. And absolutely no one anticipates that their greatest discoveries will come not from the planets, but from what lies beyond them, from a boundary that scientists thought they understood. The Voyagers weren't the first spacecraft sent toward the outer solar system. Pioneer 10 launched in 1972 and Pioneer 11 in 1973, simpler spacecraft carrying fewer instruments and no cameras capable of the detailed imaging Voyager would later provide. Pioneer 10 became the first spacecraft to cross the asteroid belt and the first to fly past Jupiter in December 1973, proving the belt could be safely traversed and that a spacecraft could survive Jupiter's radiation environment long enough to gather data. Pioneer 11 followed, using a gravity-assisted Jupiter to reach Saturn in 1979, becoming the first spacecraft to visit the ring planet. These missions were essential scouts. They tested the trajectory, validated the radiation tolerance of the electronics, and provided the first close-up data on Jupiter and Saturn that helped engineers refine Voyager's instrument design and shielding before launch. Pioneer 10 and 11 also carried their own small message to the cosmos, a gold anodized plaque showing a man and a woman and a diagram of the spacecraft's origin, a modest predecessor to the far more ambitious golden records that would fly on Voyager a few years later. Both Pioneers eventually lost contact with Earth, Pioneer 11 in 1995 and Pioneer 10 in 2003, their power sources fading in the same slow, predictable way the Voyagers would decades later. Without the pioneers proving the outer solar system was survivable, NASA might never have committed to a more ambitious four-planet grand tour on a fixed and unforgiving launch schedule. But here's what scientists in 1977 believed about the edge of the solar system. They knew the sun constantly emits a stream of charged particles called the solar wind. This wind flows outward in all directions at speeds around 250 to 500 kilometers per second. It's a plasma, a soup of protons and electrons so hot that atoms are ripped apart. The solar wind was discovered in the late 1950s and early 1960s. Eugene Parker, a physicist at the University of Chicago, predicted its existence based on theoretical calculations. He showed that the sun's corona, the outermost layer of the solar atmosphere, is so hot that it can't be gravitationally bound. The gas must flow outward continuously. Parker's prediction was controversial at first. Some scientists thought the solar wind must be transient, occurring only during solar storms, but spacecraft measurements in the early 1960s confirmed that the solar wind flows continuously. Every day, every year, regardless of solar activity level, the sun is constantly losing mass through this wind, about 1 million tons per second. That sounds like a lot, but the sun is so massive that it would take trillions of years to lose a significant fraction of its mass this way. By the time Voyager launched, scientists had learned the solar wind isn't a single uniform stream. There are two distinct components. A fast solar wind, moving toward the higher end of that range, pours out of coronal holes, dark regions in the sun's outer atmosphere where the magnetic field lines open directly into space instead of looping back to the surface. A slower, denser wind, moving toward the lower end, comes from regions closer to the sun's equatorial plane, tied to more complex, closed magnetic structures. These two streams interact as they travel outward. Since the sun's rotation sweeps the fast wind into the slower wind ahead of it, compressing the plasma and creating traveling shock fronts long before either stream ever reaches the outer solar system. This turbulent, uneven structure would later turn out to matter enormously, because it meant the pressure pushing against the interstellar medium wasn't constant. It rose and fell with the sun's roughly 11-year activity cycle, and it was this variability, more than anything else, that would make the termination shock and heliopause behave less like a fixed wall and more like a slowly breathing membrane. Parker's basic theory would go on to be confirmed with extraordinary precision decades later by NASA's Parker Solar Probe, launched in 2018 and named in his honor while he was still alive to see it, the only NASA mission ever named for a living scientist. That spacecraft would eventually fly directly through the corona itself, sampling the same wind at its source that Voyager would later sample billions of miles downstream, at the very edge of where it finally runs out of room to expand. Eventually, this solar wind has to hit something. It can't expand forever. The galaxy isn't empty. Between the stars, there's gas, extremely thin, but it's there. About 0.1 atoms per cubic centimeter. For comparison, Earth's atmosphere at sea level has about 10 to the power of 19 atoms per cubic centimeter. So interstellar space is about 10 to the power of 19 times less dense than air. It's a better vacuum than we can create in our best laboratories. But it's not nothing. Over cosmic distances, even this tenuous gas has mass, pressure, and momentum. The interstellar medium is also moving relative to the sun. Not because it has its own bulk flow past us, but because the sun is moving through it as it orbits the galactic center. From the sun's reference frame, the interstellar medium acts as a headwind. Where the solar wind meets the interstellar medium, a boundary forms. Scientists call it the heliopause, the place where the sun's influence ends and true interstellar space begins, where the outward pressure of the solar wind equals the inward pressure of the interstellar medium. Beyond the heliopause is space that's no longer dominated by the sun, space where the galactic magnetic field dominates, where galactic cosmic rays flow freely, where conditions are set by the galaxy rather than by our star. By the 1980s and 90s, scientists had built sophisticated computer models of this boundary. They ran three-dimensional magnetohydrodynamic simulations, including magnetic fields, plasma dynamics, and the effects of the sun's motion through the interstellar medium. They predicted the heliopause would be roughly spherical, maybe somewhat elongated in the direction opposite the sun's motion, forming a tail, but basically a bubble surrounding the sun at a fairly consistent distance in all directions. They calculated it should sit at about 90 to 100 astronomical units from the sun. 1 AU is the distance from Earth to the sun, roughly 93 million miles. So 90 to 100 AU meant about 8.4 to 9.3 billion miles. This seemed reasonable based on the data available. Models assumed the interstellar medium was fairly uniform in density and pressure, that the sun wasn't moving too fast through it, and that solar wind output was fairly constant, all reasonable assumptions given what was known in the 1980s and 90s. They knew the solar wind strength from measurements near Earth. They estimated the interstellar medium's pressure from astronomical observations. They ran the equations, 90 to 100 AU. That's where Voyager should cross. Before reaching the heliopause, the solar wind would encounter a shock wave called the termination shock. This happens because the solar wind is supersonic, moving faster than the speed at which pressure waves can travel through the plasma. In the solar wind plasma, the sound speed is typically around 30 to 60 kilometers per second. The solar wind flows at 250 to 500 kilometers per second, so it's moving at roughly 5 to 10 times the sound speed. It's supersonic, or more precisely supermagnetosonic, because magnetic fields also affect wave propagation in plasma. When supersonic flow encounters an obstacle, a shock wave forms ahead of it, true in air, which is why supersonic aircraft create sonic booms, and true in plasma as well. At the termination shock, the solar wind would suddenly slow from supersonic to subsonic, the plasma would heat up and compress, density would increase by a factor of 3 or 4, and energetic particles would be accelerated by the shock. Models predicted the termination shock would sit somewhere around 75 to 90 AU, somewhat closer than the heliopause itself, with the exact distance depending on solar activity, farther out during solar maximum, closer in during solar minimum. Between the termination shock and the heliopause would be a region called the heliosheath, solar wind plasma that's been slowed and heated, flowing generally outward but also sideways, trying to move around the obstacle of the interstellar medium. The flow wouldn't be smooth, it would be turbulent, filled with magnetic field irregularities and plasma instabilities, but it would still be dominated by solar material. The heliosheath was expected to be perhaps 10 to 20 AU thick. Scientists had good reason to trust this picture even before Voyager arrived, because shock waves in plasma had already been studied close to home. Earth has its own miniature version at the bow shock, the boundary where the solar wind first slams into our planet's magnetic field a few 100,000 miles upstream. A Region spacecraft had been sampling directly since the early 1960s. The physics governing that small-scale shock, the same conservation laws for mass, momentum, and energy that govern any shock front, were assumed to scale up cleanly to the vastly larger termination shock at the edge of the heliosphere. It was a reasonable assumption, essentially the same logic that lets an engineer test a scale model of an airplane wing in a wind tunnel and trust the results will hold at full size. What nobody could test in a laboratory, though, was how that shock would behave over decades, across billions of miles, exposed to a solar cycle that itself takes 11 years to complete a single swing from minimum to maximum activity and back. A wind tunnel doesn't breathe. The heliosphere does. Years after Voyager's crossings, a separate NASA mission called IBEX, the Interstellar Boundary Explorer, launched in 2008, would add another piece to this picture without ever leaving Earth orbit, by detecting energetic neutral atoms streaming inward from the direction of the heliosheath and using them to build a global map of the boundary's structure. IBEX's remote map and Voyager's direct, needle-in-the-haystack measurements agreed on the broad shape but disagreed on enough details that scientists are still reconciling the two data sets today, a reminder that even after Voyager, the picture remained incomplete. Beyond the heliopause, galactic cosmic rays would dominate, high-energy particles from supernova explosions, and other violent events across the galaxy. These are mostly blocked from the inner solar system by the Sun's magnetic field and the solar wind, but beyond the heliopause their intensity would increase significantly, perhaps doubling or tripling compared to levels at Earth's orbit. The transition across the heliopause should be fairly sharp. Models suggested it might take a few weeks to a few months at most. Solar wind plasma should disappear suddenly, galactic cosmic rays should increase, and the magnetic field should rotate as the spacecraft moved from the Sun's field into the galactic field, which was expected to be oriented differently based on the large-scale structure of the Milky Way. Scientists were confident in the basic picture. The equations of magnetohydrodynamics were well established. The physics of shocks and plasma dynamics had been studied for decades. They might be wrong about the exact distances, but the overall structure should match the models. A termination shock around 75 to 90 AU, a heliosheath 10 to 20 AU thick, a heliopause around 90 to 100 AU, a clear, relatively sharp boundaries separating solar and interstellar space. But they were wrong. Not slightly wrong, dramatically wrong. And that was just the first surprise. Understanding what makes these discoveries so remarkable requires understanding the technology that made them possible, because what Voyager accomplished, it accomplished with equipment designed and built in the early 1970s, before personal computers, before the internet, before cell phones. Each spacecraft has 3 computer systems working together. The computer command system handles instructions from Earth, the flight data system processes science data, and the attitude and articulation control system manages orientation and pointing. Together, these 3 systems have about 68 kilobytes of memory. Your smartphone has millions of times more memory than both Voyagers combined. Yet engineers can still upload software patches to these machines. In 2002, NASA uploaded new code to Voyager 1 to work around a failing memory module. In 2013, engineers switched Voyager 2 to backup thrusters that hadn't been used in 37 years, and they fired perfectly. Power comes from radioisotope thermoelectric generators, RTGs, 3 per spacecraft, which contain plutonium-238 that decays naturally and produces heat. Thermocouples convert that heat into electricity. At launch, each spacecraft generated about 470 watts, but plutonium decays over time, and power output drops steadily, about 4 watts per year. By 2026, Voyager 1 has only about 249 watts remaining. This declining power is the ultimate constraint. As power drops, engineers must decide what to shut down. The cameras went dark in 1990. By the late 2020s, there won't be enough power to run anything, and the spacecraft will fall silent. Communication happens through the Deep Space Network, 3 massive radio antenna complexes in California, Spain, and Australia, spaced around Earth, so at least one always has a view of the spacecraft. Each antenna is 230 feet in diameter. The signal from Voyager 1 takes over 22 hours to reach Earth. from Voyager 2, about 18 hours. A simple command and confirmation exchange takes over 44 hours for Voyager 1. The transmitter power from each spacecraft is about 23 watts, less than a typical LED light bulb. By the time that signal reaches Earth across billions of miles, it has faded to about 1/quintillionth of a watt, among the faintest signals humans routinely detect and decode. So how did we get here? The journey begins with Jupiter. Voyager 1 reaches Jupiter in March 1979, Voyager 2 in July 1979. The encounters revolutionize understanding of the solar system's largest planet. The Great Red Spot turns out to be a towering anticyclone rising about 5 miles above the surrounding clouds, its color coming from complex organic molecules produced when sunlight breaks down simpler compounds. Dozens of smaller storms, white ovals and brown barges, each larger than most hurricanes on Earth, interact in complex patterns governed by Jupiter's powerful winds and rapid rotation. Lightning flashes in the atmosphere, some bolts releasing 1,000 times more energy than typical lightning on Earth. Aurorae blaze at both poles, powered not by the solar wind as on Earth, but by Jupiter's own rotation and magnetic field sweeping up charged particles from Io's volcanism. Cloud bands show winds exceeding 400 miles per hour, driven by a rotation period of under 10 hours despite the planet's enormous size. But the biggest surprises come from Jupiter's moons. Io, expected to be cold and dead like Earth's moon, turns out to be the most volcanically active body in the solar system. Navigation engineer Linda Morabito spots a strange umbrella-shaped plume extending from Io's limb while examining images to pinpoint Voyager 1's position. The first active volcanic eruption ever discovered beyond Earth. Voyager finds 9 active volcanoes during the flybys. Later observations catalog over 400 volcanic centers. The activity comes from tidal heating, Jupiter's enormous gravity, combined with tugs from Europa and Ganymede, constantly flexes Io's interior, generating friction and heat, a process theorized but never confirmed until Voyager. This discovery reshapes how scientists think about energy sources for geology, showing that tidal heating from gravitational interactions, not just radioactive decay, can drive volcanism and tectonics, relevant to Io, Europa, Enceladus, and potentially exomoons around giant exoplanets. Europa presents a different mystery. A smooth icy surface, crisscrossed with cracks and ridges, with very few craters suggesting a young, constantly renewed surface. Long linear cracks and regions of chaotic terrain hint that beneath the ice might be a liquid water ocean, kept liquid by a gentler version of the same tidal heating affecting Io. Voyager can't prove the ocean exists. The evidence is circumstantial, but it's the first suggestion that an icy moon might hide an ocean, a possibility that later missions, like Galileo, would strengthen, and that continues to drive mission planning today. Ganymede, the largest moon in the solar system, shows old, heavily cratered terrain alongside younger terrain with grooves and ridges, suggesting past geological resurfacing. Callisto, the outermost Galilean moon, is heavily cratered and ancient, its surface apparently unchanged for billions of years, a stark contrast to Io. Voyager also discovers that Jupiter has rings, faint, dust-sized, nothing like Saturn's spectacular ice rings, suggesting ring systems might be common around giant planets, some spectacular, others faint. The Jupiter flybys are also where the mission encounters its first genuinely dangerous environment. Jupiter's magnetic field is by far the strongest of any planet in the solar system, and it traps charged particles into radiation belts far more intense than the Van Allen belts surrounding Earth. Passing through the inner belts exposes each spacecraft to radiation doses that engineers had modeled carefully beforehand but still approach with real uncertainty, since no previous mission had carried instruments this sensitive this close to Jupiter for this long. The radiation is intense enough to have visibly degraded some of Voyager's camera electronics during the encounter, introducing streaks and noise into a handful of images, and it remains one of the reasons later missions to Jupiter, including Galileo and Juno, were designed with additional shielding around their most sensitive electronics. Voyager also gets a close look at Amalthea, a small, dark, oddly reddish moon orbiting well inside Io's orbit, and confirms that Jupiter's magnetosphere is so enormous that, if it were visible to the naked eye from Earth, it would appear larger in the sky than the full moon, a bubble of magnetic influence stretching millions of miles beyond the planet itself and, at its farthest extent, well past the orbit of Saturn. By the time the Voyagers leave Jupiter, they've returned more data than all previous observations combined, and Saturn is next. Voyager 1 reaches Saturn in November 1980, Voyager 2 in August 1981. Saturn's rings had been known since Galileo first observed them in 1610, though he didn't understand what he was seeing. By the 1980s, astronomers knew Saturn had multiple rings separated by gaps, but had no idea of the true complexity. Voyager reveals each visible ring is actually made of thousands of individual ringlets, structure far finer than anything resolvable from Earth. The rings aren't solid. They're made of billions of individual particles ranging from dust grains to house-sized boulders, each orbiting independently. The rings show waves, braids, kinks, and mysterious dark radial spokes that rotate with the rings, later attributed to electrostatic levitation of dust above the ring plane. Shepherd moons. Tiny satellites orbiting near ring edges, herd ring particles, and maintain sharp boundaries through their gravity. Prometheus and Pandora flank the F-ring, keeping it confined and producing a braided structure unlike anything seen elsewhere. Density waves and bending waves, driven by gravitational resonances with Saturn's moons, propagate through the rings and create spiral patterns and vertical warping. And despite spanning thousands of miles across, the rings are astonishingly thin. Only about 30 feet thick in most places. Titan, Saturn's largest moon, was already known to have a thick atmosphere, the only moon in the solar system with one comparable to a planet's. Voyager 1 makes a close flyby, passing within 2,500 miles, sacrificing the trajectory that would have let it continue to Uranus and Neptune, which is why Voyager 2 takes over for the ice giants. The atmosphere turns out even thicker than expected, with surface pressure about 1.5 times Earth's, composed primarily of nitrogen with methane and other organic compounds, ethane, propane, acetylene, driving complex atmospheric chemistry. The surface is hidden beneath an opaque orange photochemical haze made of tholins, complex organic molecules similar to compounds that may have existed on early Earth. Voyager's cameras can't see through to the surface, but atmospheric data suggests Titan has a methane cycle analogous to Earth's water cycle, with likely lakes or seas of liquid methane and ethane on the surface, later confirmed by the Cassini mission and the Huygens probe, which landed on Titan in 2005. Titan isn't the only Saturnian moon that surprises scientists. Mimas, small and heavily cratered, turns out to be dominated by a single enormous impact crater roughly a third of the moon's own diameter, with a central peak and steep walls that give the little moon an unmistakable resemblance to a fictional battle station, an impact so large that a slightly bigger one would likely have shattered the moon entirely. Iapetus shows one of the strangest surfaces in the solar system, with one hemisphere almost as dark as asphalt and the other nearly as bright as fresh snow, a contrast so extreme that Giovanni Cassini, observing Iapetus from Earth in the 17th century, had noted it could only be seen on one side of its orbit and correctly guessed the moon must have two very differently colored faces. Voyager's images don't fully settle why the contrast exists, though later missions would attribute it to a combination of dark dust swept up from an outer moon and a runaway thermal process that causes ice to migrate away from the darker regions. Rhea, Saturn's second-largest moon, shows a heavily cratered, icy surface generally similar to Callisto's, reinforcing the idea that some icy moons simply freeze in place billions of years ago and stay that way. None of the Saturnian moons show anything like the plume activity later discovered at Enceladus by the Cassini mission in the 2000s. Voyager's cameras catch no hint of it, a reminder that even a spacecraft returning tens of thousands of images can still miss a major discovery sitting in plain sight, waiting for a mission with better instruments or a more fortunate flyby geometry. After Saturn, the two Voyagers diverge. Voyager 1 heads above the solar system plane toward interstellar space, visiting no more planets. Voyager 2 continues to Uranus and Neptune, the only spacecraft to visit either, and still the only one to this day. Voyager 2 reaches Uranus in January 1986. Uranus's axis is tilted 98 degrees relative to its orbital plane, so it essentially rolls along its orbit rather than spinning like a top, giving each pole 42 years of continuous daylight followed by 42 years of darkness. The atmosphere proves surprisingly bland, few visible cloud features, a pale blue color from methane absorbing red light, winds reaching 560 miles per hour, 10 previously unknown moons, and 2 new rings. The most interesting discoveries come from the moon Miranda, whose surface shows bizarre juxtapositions of ancient cratered terrain next to grooved terrain and enormous cliffs, including Verona rupees, estimated at about 6 miles high, over 3 times the height of the walls of Valles Marineris on Mars. The cause remains uncertain, though theories range from a catastrophic impact that shattered and reassembled the moon to past tidal heating. Uranus delivers one more surprise that has nothing to do with its moons. Its magnetic field turns out to be tilted about 60 degrees away from the planet's already sideways rotational axis and offset substantially from the planet's actual center rather than aligned through it, unlike every other planetary magnetic field measured up to that point, which tend to roughly follow the rotation axis the way Earth's does. The likely explanation is that Uranus's magnetic field isn't generated in a metallic core the way Earth's or Jupiter's is, but in a deep layer of electrically conductive, highly compressed water, ammonia, and methane slush, a fundamentally different kind of dynamo than anything studied at close range before. Voyager also gets a look at Uranus's 4 other major moons. Aerial and umbreal, mid-sized icy bodies with surfaces that hint at some past geological activity in Ariel's case, and almost none in Umbriel's, and Titania and Oberon, the 2 largest, both heavily cratered with hints of enormous canyons suggesting the icy crust cracked and shifted at some point in the distant past. Compared to Miranda, none of them attract nearly as much attention, but together they establish that even the coldest, most distant moons in the system don't share a single uniform history. Some froze early and stayed that way, and others clearly didn't. Voyager 2 reaches Neptune in August 1989, nearly 3 billion miles from Earth, the culmination of the Grand Tour, 12 years after launch. Neptune, expected to resemble a bland Uranus, instead shows the most dynamic atmosphere of any planet visited, the Great Dark Spot, an Earth-sized storm, a bright cloud feature nicknamed the Scooter, circling the planet every 16 hours, and winds exceeding 1,300 miles per hour, the fastest measured on any planet in the solar system. Neptune's largest moon, Triton, orbits in a retrograde direction, opposite to Neptune's rotation. Extremely unusual for a large moon and strong evidence it was captured, probably from the Kuiper belt, rather than forming alongside Neptune. Triton also shows active nitrogen ice geysers erupting from one of the coldest surfaces in the solar system, likely driven by seasonal sunlight warming dark subsurface regions until built-up nitrogen gas ruptures the surface. Neptune also turns out to have rings, something ground-based observations in the years before the flyby had hinted at but couldn't confirm, since earlier stellar occultation experiments, watching a background star's light blink as Neptune passed in front of it, sometimes showed a dip and sometimes didn't, exactly as would happen if the rings were clumpy rather than complete. Voyager's images solved the mystery, revealing faint, narrow rings with distinct dense arcs, clumps of material bunched together within an otherwise sparse ring, held in place by the gravitational influence of a small nearby moon in much the same way Saturn's shepherd moons confine its F-ring. Voyager also images Nereid, a small moon on a wildly elongated, distant orbit unlike any other large moon in the solar system, and discovers several other small inner moons, including Proteus, closely orbiting and irregularly shaped, that had never been seen from Earth at all. With Triton's retrograde orbit as the centerpiece, Neptune's moon system as a whole paints a picture of a system disrupted at some point in its history, most likely when Triton was captured from the Kuiper belt, and its arrival gravitationally scattered whatever smaller moons had originally formed alongside Neptune. With Neptune, Voyager 2's planetary mission ends. Both spacecraft had far exceeded their original goals. Active volcanism on Io, hints of a subsurface ocean on Europa, Jupiter's rings, thousands of ringlets in Saturn's rings, Titan's thick atmosphere, Miranda's bizarre geology, Neptune's record winds, Triton's geysers, and they were still functional. So NASA made a decision. The Voyager interstellar mission would begin, sending the spacecraft onward toward the boundary where the sun's influence ends. No spacecraft had ever gone that far. Scientists had models and predictions. Nearly all of them would turn out to be wrong. The Voyager discoveries also carry sobering implications for future interstellar travel, since they give us the first direct measurements of the environment any interstellar spacecraft would have to cross. Voyager 1 has been traveling for nearly 50 years and has covered about 159 AU, 14.8 billion miles. That sounds impressive until compared with the distance to even the nearest star, Proxima Centauri 4. 24 light-years away, about 268,000 AU, roughly 25 trillion miles. At Voyager speed, reaching Proxima Centauri would take about 73,000 years, and Voyager isn't even headed in that direction. The star it will pass closest to, Gliese 445, is still 1.6 light-years away at closest approach, in about 40,000 years, nowhere near actually entering that star's system. These time scales reveal the fundamental challenge. To make interstellar travel remotely practical, spacecraft would need to reach at least a few percent of light speed, maybe around 10% for reasonable travel times to nearby stars. At 10% of light speed, Proxima Centauri would be about 42 years away, a human lifetime, but achievable within a career. Reaching that speed, however, requires enormous energy, and Voyager's discoveries reveal additional challenges along the way. The interstellar medium, though extremely tenuous at about 0.08 atoms per cubic centimeter, becomes a real hazard at high velocity, since kinetic energy of impact scales with velocity squared. A spacecraft with a 1 square meter cross-section traveling at 10% of light speed would be struck by roughly 100 trillion hydrogen atoms per second, depositing several thousand watts of heat continuously, and causing cumulative radiation damage to materials and electronics over years. Cosmic ray exposure, measured by Voyager at about twice the level in interstellar space compared to the inner solar system, adds further hazard, since high-energy cosmic rays penetrate deep into materials and would require significant shielding for any crewed mission or sensitive electronics. The magnetic field measurements matter too, since charged particle trajectories and potentially magnetic sail propulsion concepts depend on the strength and orientation of the interstellar field, now measured directly for the first time. The tsunami wave detections reveal that interstellar space isn't quiescent, Shock waves from solar and stellar outbursts propagate for billions of miles, meaning a future interstellar spacecraft might periodically encounter disturbances from distant stars along its path. The heliosphere's newly measured shape and size also matter for mission planning, since the distance to interstellar space depends heavily on direction, anywhere from about 120 AU to well beyond. And beyond the heliopause lies the Oort cloud, a hypothetical shell of icy objects thought to extend from roughly 2,000 AU out to perhaps 100,000 AU, halfway to the nearest star. Voyager 1 won't reach its inner edge for about 300 years, and won't exit the outer edge for roughly 30,000 years, meaning any interstellar mission, even traveling far faster than Voyager, would spend the bulk of its journey still technically within the Sun's gravitational sphere of influence, in territory we know almost nothing about. The Oort cloud has never been directly observed. Its existence is inferred indirectly, largely from the orbits of long-period comets, icy bodies that occasionally fall inward toward the Sun on trajectories consistent with originating from a vast, roughly spherical reservoir far beyond the planets, gently perturbed out of stable orbits by the gravitational tug of passing stars, or the wider galaxy over billions of years. No spacecraft has ever imaged an Oort cloud object directly, and basic questions about it remain unanswered. How much total mass it contains, whether its objects are uniformly distributed or clumped, and whether Voyager 1 or 2 will pass close enough to anything out there to be affected by it at all. It's entirely possible that both spacecraft will simply drift through billions of miles of that hypothesized territory without incident, just as they've already drifted through the enormous, largely empty stretch of space beyond the planets, and just as they'll drift through the even vaster true interstellar space that follows it. None of this makes interstellar travel impossible. But it does mean the technologies required, from propulsion to shielding to power to communication across light years, remain far beyond what we currently possess. Perhaps the Voyager's greatest contribution to that future is simpler, proof that something built by humans can leave the solar system and keep working for decades in an environment this hostile. On February 14, 1990, Voyager 1 turned its camera backward for one last look at the solar system from about 3.7 billion miles out, capturing a family portrait of 6 planets. In one of those images, Earth appears as a single pale blue pixel suspended in a scattered beam of sunlight, the image that inspired one of the most widely quoted reflections on humanity's place in the cosmos, the idea that every human life, every triumph and tragedy, played out on that single mote of dust. The spacecraft that captured that image went on to cross the heliopause and measure the galaxy beyond the Sun's influence, a reminder of just how small the entire solar system is within the vastness of interstellar space, and a reminder that if we're still learning basic facts about the boundary of our own solar system, there is enormously more still to learn farther out. By 2026, nearly 50 years after launch, both Voyagers remain operational, but they are dying. Voyager 1 is currently about 159 AU from the Sun, roughly 14.8 billion miles, with signals taking over 22 hours to reach Earth. Voyager 2 is about 132 AU out, roughly 12.3 billion miles, with an 18-hour signal delay. Both are moving at roughly 38,000 miles per hour relative to the Sun. Voyager 1 gains about 3.6 AU of distance per year, Voyager 2 about 3.3 AU. The power situation is critical. In 2026, Voyager 1 has about 249 watts remaining against a roughly 245 watt requirement to keep core systems and instruments running, a margin of only a few watts. Every few months, engineers shut down another heater or move a system to standby. In 2020, NASA shut down the heater for Voyager 2's cosmic ray instrument, expecting it to fail once it dropped to -74 degrees Fahrenheit. Instead, 1970s engineering kept working 40 degrees below its design temperature. But time is running out. By around 2025 to 2027, there won't be enough power to run core systems alongside any science instruments, and engineers will begin permanently shutting instruments down. By roughly 2030, possibly as late as 2032, the power budget will be exhausted, transmitters will fall silent, and the spacecraft will continue drifting, intact, but dead, with no way to communicate. They'll keep drifting for an almost incomprehensible span of time. Voyager 1, heading generally toward the constellation Ophiuchus, will pass within about 1.6 light-years of the star Gliese 445 in roughly 40,000 years. Voyager 2, heading toward the constellation Pavo, will pass within about 1.7 light-years of the star Ross 248 around the same time. Neither will enter those star systems, just drift past in the emptiness between stars. Over millions of years, gravitational encounters with other stars will gradually reshape their trajectories. Over billions of years, they'll orbit the galactic center along with everything else, once every roughly 225 million years. Each Voyager carries a golden record, a 12-inch gold-plated copper disc containing sounds and images from Earth, designed to remain intact and readable for hundreds of millions, possibly billions, of years, since gold doesn't corrode in the vacuum of space and the information is physically etched rather than stored electronically. The sounds were chosen to represent Earth's diversity, natural sounds like wind, rain, thunder, surf, and volcanic eruptions, the songs of humpback whales, birdsong, human sounds including a baby crying, footsteps, laughter, and a heartbeat, the sounds of tools and transportation, from a hammer on an anvil to a rocket launch, and music spanning cultures and centuries, from Bach and Beethoven to traditional Javanese gamelan, Senegalese percussion, Aboriginal Australian song, Peruvian panpipes, Chinese and Indian classical traditions, blues, jazz, and rock and roll. Selecting that music was, by all accounts, the most difficult part of the project. An attempt, inevitably imperfect, to represent the full range of human culture on a single disc, led by a committee that debated and compromised over every inclusion, aware that each choice meant something else had to be left out. The committee, assembled and led by astronomer Carl Sagan, included a science journalist, a composer, and several other collaborators, and they worked against a genuinely inflexible deadline, since the launch windows dictated by the planetary alignment couldn't simply be pushed back to accommodate more deliberation. The inclusion of Chuck Berry's Johnny B. Good drew criticism at the time from some who felt rock and roll was too frivolous a genre to represent humanity to another civilization, a tension the committee resolved by including it anyway, alongside Bach, Beethoven, and traditions from 6 continents, on the reasoning that leaving out an entire category of human expression would be its own kind of distortion. Physical constraints shaped the record as much as any philosophical debate. The grooves could only hold so much analog information, so every additional minute of music or every added image meant either lowering the audio quality across the board or cutting something else already selected. The team reportedly finished assembling the final content only shortly before the discs needed to be manufactured and mounted onto the spacecraft. The record's aluminum cover carries its own small puzzle, designed to be solved by whoever eventually finds it without any assumption they'd share a language, or even a sensory system, with the people who made it. Diagrams etched into the cover show the correct playback speed using a binary time unit derived from a fundamental property of hydrogen, the most abundant element in the universe, and therefore a plausible common reference point for any technological civilization. Other diagrams show the stylus and cartridge needed to trace the grooves, and how to convert a portion of the audio signal back into a sequence of still images, essentially a visual instruction manual with no words at all, built entirely from physics and geometry on the assumption that mathematics might be the only truly universal language available. The record also carries spoken greetings in 55 languages, from long-dead tongues like Akkadian and Sumerian to modern languages spoken by billions, each offering a brief message of peace and friendship. And it carries 116 images, encoded as audio waveforms rather than stored as pictures directly. Mathematical definitions, chemical structures, DNA, the solar system, Earth from space, landscapes, human anatomy, families, cities, art, and technology, decodable using instructions etched in pictograms on the record's aluminum cover, alongside a map showing Earth's location relative to 14 pulsars, whose slowly changing periods effectively timestamp when the record was made. Creating it was an enormous collaborative effort completed under a tight, inflexible launch schedule involving scientists, artists, musicians, linguists, and anthropologists, and it amounted to more than a scientific project, an attempt to answer, under real constraints and real disagreement, what's worth saying about being human to someone who knows nothing about us. The odds that the record will ever be found are, by any reasonable estimate, essentially zero. Space is too vast, the Voyager's too small, and neither spacecraft is aimed at any particular star. But the value was arguably in the act of creating it, in being forced to decide what matters, what's universal, and what we'd want to say if we only had one chance to say it. The Voyager program's total cost through the Neptune encounter was roughly $865 million, a remarkably small investment for the return. For planets explored in detail, dozens of moons studied, the first observations of volcanism beyond Earth, the first hints of a subsurface ocean on an icy moon, the first measurements of the termination shock, the first crossing of the heliopause, and the first direct sampling of the interstellar medium. Every one of the 7 major findings beyond the heliopause required scientists to revise their models and reconsider their assumptions. Not because the original predictions were careless, but because the universe is more complex than any model can fully capture. That's the value of exploration, not simply confirming what we already believe, but discovering what we didn't know. NASA is now considering a follow-up mission called the Interstellar probe, still in the concept stage with no confirmed launch date or budget. The goal would be to reach 500 to 1,000 AU within about 50 years. 5 to 10 times farther than the Voyagers have traveled, requiring speeds roughly twice Voyager's or more, likely through a closed solar flyby and advanced propulsion. Its science goals would directly follow up on what Voyager found, mapping the heliosphere's nose and tail in more detail, searching for the predicted bow shock, and gathering more comprehensive measurements of the interstellar medium, galactic magnetic field, and cosmic rays than 2 single-trajectory spacecraft ever could. Even in the best case, the mission likely wouldn't launch before the 2030s, and wouldn't reach 500 AU until the 2080s, meaning many of the scientists designing it today won't live to see its primary results. That's the nature of exploration on these time scales. It requires institutional commitment across generations, a willingness to start something whose conclusion you may never see. The interstellar probe concept, even if funded, would still only be a faster, farther-reaching cousin of Voyager, a mission designed to sample the boundary more thoroughly, not to travel to another star. True interstellar travel, reaching even a meaningful fraction of light speed, would require an entirely different category of propulsion than anything flown to date, and several concepts have been proposed over the decades, none of them close to realization. Project Orion, studied in the 1950s and 60s, envisioned propelling a spacecraft by detonating a series of small nuclear explosives behind it, an idea abandoned partly for engineering reasons and partly because atmospheric nuclear testing bans made even ground testing the concept legally impossible. Project Daedalus, a 1970s design study by the British Interplanetary Society, proposed a fusion-powered spacecraft intended to reach roughly 12% of light speed, fast enough to reach a nearby star system within a human lifetime, but dependent on fusion technology that remains unrealized even in ground-based power plants decades later. More recently, the Breakthrough Starshot initiative has proposed an entirely different approach. Not a single large spacecraft, but a fleet of grand-scale probes attached to light sails, accelerated by a ground-based laser array to perhaps 20% of light speed over just minutes, potentially reaching Proxima Centauri in about 20 years rather than tens of thousands. The concept sidesteps the fuel problem entirely by leaving the propulsion system behind on Earth, but it introduces enormous unsolved challenges of its own, from building a laser array powerful enough to do the accelerating, to designing electronics durable enough to survive that acceleration and then function usefully after decades of interstellar cruise. Exposed to exactly the kind of dust and radiation environment the Voyagers first characterized. None of these concepts currently has a funded, active spacecraft in development. What they share is a dependence on the same basic physics the Voyagers helped clarify: how dense the interstellar medium really is, how much radiation a spacecraft will absorb crossing it, and how far a mission actually has to travel before it's meaningfully clear of the sun's influence. Part of what made the mission's long survival possible was an unusual continuity on the human side of the project, not just the hardware side. Ed Stone, a physicist at Caltech, served as the mission's project scientist from before launch in 1972 all the way through 2022, exactly 50 years, overseeing the science team through every planetary encounter, every unexpected discovery, and every budget review in between. That kind of continuity is rare in a field where careers, funding cycles, and even entire subfields of study typically turn over every few years. It meant that when the confusing, contradictory heliopause data started arriving in 2012, the team interpreting it included people who had been working with these two spacecraft, and with each other, for decades, who understood the quirks and failure modes of instruments that were themselves older than most of the graduate students now analyzing their output. The engineering team faces a similar, stranger challenge. Many of the original Voyager engineers have since retired or passed away, and current mission operators sometimes have to consult decades-old paper documentation, or even track down retired engineers directly, to understand design decisions made in the early 1970s using tools and conventions that predate most modern software engineering practice entirely. Commanding the spacecraft today occasionally involves relearning programming languages and command structures that haven't been actively used anywhere else in the world for half a century. Whether or not that mission ever launches, what the Voyagers already discovered is permanent. The measurements exist in NASA's archives. The data has been folded into our scientific understanding, and it will keep being studied for decades, likely yielding insights no one has noticed yet. Two spacecraft launched in 1977, with computers less powerful than a modern calculator, built to last 5 years, are still operational nearly 50 years later. They gave us the first close look at volcanism beyond Earth, the first hints of an ocean hidden under ice, the full complexity of Saturn's rings, our only close-up data on Uranus and Neptune, and then, almost as an afterthought to their original mission, they crossed a boundary no spacecraft had ever reached and measured interstellar space directly for the first time. Every specific prediction about that boundary turned out to be wrong in some way. The heliopause sat billions of miles farther out than expected. Its shape was asymmetric rather than spherical. The transition took years instead of weeks, and included a structure, the magnetic highway, that no model had anticipated. The interstellar medium's density, temperature, and pressure all differed slightly from estimates. The galactic magnetic field's orientation surprised researchers, and turn out to vary meaningfully over relatively short distances. Cosmic rays arrive from unexpected directions. Not one of these findings broke the underlying physics. The basic picture of a solar wind meeting an interstellar medium at a pressure balance boundary held up. But every specific, quantitative detail needed to be revised. That, in the end, is what these two aging spacecraft really taught us. That even in our own cosmic backyard, at a boundary we thought we understood well enough to model with confidence, reality still had surprises left to offer. The plutonium in their power sources keeps decaying, a few watts every year, and sometime around 2030 the last transmission will fade into the background noise, and the deep space network will stop hearing anything from that point in the sky. The spacecraft themselves will keep moving at 38,000 miles per hour, carrying their golden records outward for as long as the galaxy exists, whether or not anyone is ever there to find them. Proof that a species that had existed for a few 100,000 years once built something that worked well enough, and long enough, to leave home and tell us what was actually out there.